Okay, so the goal of this presentation is to point out some tips on how to produce the leading ones if they are not already in the first column. So these are just some tips on finding the row echelon form or the reduced row echelon form. If you notice in the previous two lectures, the matrices that I used had an easy or obvious way to produce the leading ones. For example, if you look at the first column, if you already have a leading one, if it's not already in the first position, but if you have a 1 in the first column, a simple interchange will place that leading 1 in the right position. So the goal is to have a 1 here instead of 2. Now, if you don't have a 1 already, okay, so just to make it clear, the whole point of this presentation is how to produce the leading ones in an efficient way, because there is an easy way or a hard way to go about it. Because these are algorithms, these steps of row operations to produce the row echelon form, these are standard algorithms. There is a desire to make a universal step on accomplishing a task. But we have our brain and we have to be flexible to make our life easier. So in the first part of the presentation, I'm going to talk about the standard step in producing a leading one and point out what is the disadvantage or why sometimes that makes it tedious as you move along. So the standard step is to simply divide the row by the leftmost non-zero entry. In this case, by 2. So whatever the first non-zero entry on that row is, if you need a leading 1 in that position, you just divide it by that entry and you can produce 1. Now, unfortunately, that sometimes introduces fractions, which is the stuff that makes the computation harder. And I'll show you in the second part how you can avoid it sometimes, often actually. I mean, there are a few cases when you cannot avoid fractions, but if you can, you should be flexible with these row operations. So the standard step that always works in principle, except that you're going to have fractions to deal with often. In this case, like I said, is to divide the first row by half, by 1, so to divide it by 2. So that makes the first row 1 minus 3 over 2, 3 over 2, and 1, 2 over 2. So we made the one that we needed in the right position, but now we have to handle fractions pretty much till the end. And for that reason, we're going to need, as you'll see later, you're going to need some scratch paper because you need to have these numbers in the exact format. If you use the calculator and it gives you decimals, that's not going to be helpful. So if you have to do it by hand, be prepared to take the computations separately when you handle these row operations. So obviously the next step here in the process is to replace row 2 by minus 3 row 1 plus row 2 and row 3 by minus 4 row 1 plus row 3. The stuff you can do in your mind, you can do it, but when you handle the fractions, like I said, it's better to just take them separately. So minus 3 times 1 plus 3 is 0 to the scratch paper. So on this second entry, I have minus 3 over 2 multiplied by minus 3 plus 1. That's 9 over 2 plus 1. That's 11 over 2. Okay, so I have 11 over 2 on the second position on the second row. Moving along, we have 3 over 2 times minus 3 minus 2. That's minus 9 over 2 minus 2. 9 minus 4 makes it minus 13 over 4. Minus 13 over 2, I'm sorry. Minus 13 over 2. Last entry, we could do that in our minds. 1 times minus 3 plus 2, that's minus 1. Last row, minus 4 times row 1. Minus 4 times 1 plus 4, that's 0. Scratch paper again. Minus 4 minus 3 over 2 minus 2. 12 over 2, that's 6. Minus 2 makes it 4. And minus 4 times 3 over 2 minus 2. excuse me, plus 1, not minus 2. I was looking at the second row again. So 3 over 2 times minus 4 plus 1. That's minus 6 plus 1 makes it minus 5 over here. Last entry, 1 times minus 4 plus 3, that's minus 1. All right. Again, the standard step. We have 11 over 2. We need 1. If we use the standard step that I said before, it means that we need to multiply row 2 by the reciprocal to make it 1. Divide by 11 over 2 is the same thing as multiplying row 2 by 2 over 11. And now the matrix is 1 minus 3 over 2, 3 over 2 and 1, 0, 1. Let's see, minus 13 over 2 times 2 over 11 makes it minus 13 over 11. And then minus 1 times 2 over 11 makes it minus 2 over 11. Copy the last row for now. We have the leading ones. We need 0 below the second leading one. So we need 0 instead of 4. So the way to do this is minus 4 row 2 added to row 3. Keep the second row as it is. 0, 1 times minus 4 plus 4 is 0. Scratch paper again. Minus 4, minus 13 over 11, minus 5. That's 52 over 11 minus 5. Makes it minus 3 over 11. And the last entry is minus 4 minus 2 over 11. And then minus 1, that's 8 over 11 minus 1, makes it again minus 3 over 11. This is the kind of stuff you need to do, and you should take the time to do it for practice on your own. Do the computations, don't just copy. By the way, imagine you're my grader. That's the best way I can put it. Don't just watch my computation, pause the video and act as if you're checking my work. And in fact, if you notice a typo, you can put it in the comment. But imagine your grade. In fact, don't just imagine it. Just grade my work, essentially. Okay, don't trust my computation. Do it on your own, because that's basically the way you actually practice for real, not just watching it. Anyway, last row, because we need to make a 1 on the last row, is to multiply. And by the way, in this case, that's the only way to do about it. I mean, there's no, because you cannot touch row 1 and row 2. The only way to produce the last leading one is to multiply by minus 11 over 3. The reciprocal of that, minus 3 over 11, to make it a 1. And we finally arrive to the row echelon form. All right, so that's going to be 0, 0, 1, 1. So funny enough, actually, you'll see the system doesn't have a complicated solution. It's just that using the standard step that I mentioned, we had pretty tedious process to get to the row echelon form. So the system is x minus 3 over 2 y plus 3 over 2 z equals 1. Second equation is y minus 13 over 11 z equals minus 2 over 11. And the last equation is z equals 1. As you substitute z in the second, y is 30 minus 2 over 11, that's 1. And go back to the first equation, replace y with 1, z with 1, that makes x equals 1. So the solution is x equals 1, y equals 1, z equals 1. Okay, so I hope this part is enough motivation for you to learn to be flexible with the row operations so that you can avoid this mess if possible. You will see in the second part, we could do the same problem all the time, avoiding fractions. So don't go by the standard step unless you can, I mean, if you can do the same thing more efficiently. Remember, you can use any number of row operations and any row operations you like at any step. use it wisely, and as a principle, try to avoid fractions if you can. You will see that in the second part, we accomplish the same thing. The row echelon form will be different and easier because I should have mentioned last time, row echelon form is not unique. It depends on the row operations that you use to accomplish the row echelon form, and the row operations can be different to accomplish the same thing. So the row echelon form is not unique. Now the reduced row echelon form is the same if you are to decide to go up to the reduced row echelon form, but the REF actually depends on the path you choose. I mean, depends on the row operations you choose. So stay tuned for the second part when we do the same example, but this time around avoiding fractions altogether. Okay, so same exercise, and let's see how we can actually avoid fractions. So this time we're going to try to do the same thing, producing the row echelon form and solving the system, but can we avoid fractions altogether in producing these leading ones that we need? This is where you should be flexible with row operations if possible. So like I said before, the temptation is to say, okay, I have 2 in this position, I need to make it a 1, I'll just divide the whole row by 2 because I need 1 on that position. But that introduces, of course, fractions, which will make the computation more tedious. Always remember that you have 3 row operations at your disposal, and the workhorse of all row operations is the one in which you can multiply a row by a certain constant and add it to another row. So instead of dividing by 2, we can exploit the relationship between 3 and 2 for row 1 and row 2, and realize that if I subtract row 1 from row 2 and place row 2 in the first position, I'll produce a leading one without fractions. So basically row 2 becomes row 2 minus row 1. That's one of the allowed row operations. And then I'll make an interchange between row 1 and row 2, which will produce the leading one in the position that I want. So we could do these both row operations at the same time. 3 minus 2 is 1, so I'll do the interchange on the same step. 1 minus negative 3 makes it 4. Minus 2 minus 3 is minus 5. 2 minus 2 is 0. And then the old row 1 becomes the new row 2. And there it is. We have a leading one without introducing any fractions. Okay, so the second 2 steps are the same as before. You produce zeros below the leading one. So you need to change row 2 to be minus 2 row 1 plus row 2. And row 3 becomes minus 4 row 1 plus row 3. And the new matrix is 0. So 1, 4, minus 5, 0. Then 0, let's see, minus 2 times 4 minus 8 minus 2, that's minus 11. Then 13, minus 2 times minus 5 is 10, plus 3 is 13, and then minus 2 times 0 plus 2, that's 2. Minus 4 times 1 plus 4 is 0. Minus 4, that's 16. So minus 16 minus 2 makes it minus 18. And then minus 4 minus 5, that's 20, plus 1, 21. And then this remains 3, minus 4 times 0 plus 3. Okay, now we need a leading one in place of minus 11. Again, don't rush to divide by minus 11, because again, you introduce fractions. Now I want to emphasize sometimes, and maybe we should write it down here, sometimes fractions cannot be avoided. But it pays off to actually think about row operations to see if you can actually avoid them, because you end up spending less time. So for example, at the very least, let's actually do an extra step here, which is not part of the algorithm per se. I mean, not part of the algorithm necessarily, but just to make the coefficient smaller. So for example, I noticed that the last row is a multiple of 3. Let's just make the coefficient smaller by dividing the third row by 3. Nothing wrong with that. So we have 0 minus 18 over 3 is minus 6. 21 over 3 is 7, 3 over 3 is 1. So can I make a row operation to avoid fractions so I can place a leading 1 instead of minus 11? Well, this might be less obvious than the first step when I exploited the relationship between 2 and 3. So I noticed that the difference between them will produce 1. But if you look carefully and with some experience, you again can avoid fractions. Because if I multiply minus 6 by minus 2, I'll produce a 12. So if I add it to the second row, that's the one that I need. Again, it takes a little bit of practice to figure these steps out, but it pays off to think about these steps. So what I'm going to do is I'll replace row 2 by minus 2 row 3 plus row 2. Minus 2 times minus 6 becomes 12, right? So the whole point of doing this is because this will give me the leading 1 in the proper position. So the first row again is unchanged. Now I have 0, 1, and now I have to be careful. So minus 2 times 7, that's minus 14, plus 13, that's minus 1. And minus 2 times 1 plus 2, that's 0. And let's copy the last row. I have the 2 leading ones. All I need now is 0 below the second leading 1. To do that, we need row 3 to be replaced by 6 times row 2 added to row 3. So the new augmented matrix now is 0, 1, excuse me, 0, 0, right? So 6 times 1 minus 6. Minus 6 plus 7 is 1, and then minus 6 times 0 plus 1 is 1. Let's leave it at that. I was gonna think about moving on to reduce our echelon form, but let's not make this longer than necessary. So this is the REF, just like before. And I should point out that, notice that's another important observation. So the REF, the reduced row echelon form, is not unique. So you could go via various methods in producing the row echelon form, and you can have a row echelon form of the matrix different than the other. So the row echelon form is not unique. The reduced row echelon form is the same in all cases, but the row echelon form is not unique depending on the row operations you perform. Okay, so now the system is much easier to solve. The system is x plus 4y minus 5z equals 0, y minus z equals 0, z equals 1. Z equals 1, plug it back into the second equation, that gives me y equals 1. Plug it back into the first equation. That gives me x equals 1 as expected. So the solution is x equals 1, y equals 1, z equals 1. So with that, the last thing I want to mention is, when you avoid fractions, it's not necessarily the case that you do fewer row operations. In fact, you could do actually more row operations than before because of, trying to simplify these things. Like for example, this step here, when I introduced the row operations just to make those coefficients smaller. However, it should feel easier and faster as long as you don't involve fractions. So the bottom line, or the main message to be taken from here, is that as long as you perform the row operations correctly, you can do any row operation you want at any step in the process you want. Use these row operations to your advantage, with always thinking about how to do the process more efficiently, so that you don't spend too much time. The whole point of the algorithm is to solve a lengthy problem in an efficient way. So that's all I have for now.